our next speaker is Dominic Ellis.
This talk is going to be about this idea of quantum computation, this idea that by building devices which exploit the laws of quantum mechanics in some fundamental way, you can get computational speedups for certain problems. To do this, one of the things you need is quantum entanglement. And so normally, the traditional approach to this would be you create entanglement somehow along the way, along your process. And in doing this, you're essentially driving your systems out of equilibrium. So your systems don't really want to be entangled. There will be all kinds of relaxation processes acting on those systems, trying to make them into their equilibrium state, which is not an entangled state, and you have to fight that somehow. So I'm going to be talking about a different approach, which is the idea that you can have quantum systems which, in their equilibrium state, are entangled. And in particular, we consider quantum spin systems of interacting spins, such that their ground state, that is their low temperature equilibrium state, is entangled. So here are some of the models which people have talked about in relation to this. The problem with the thing about all these models is that they're specifically constructed so that they have special properties which allow you to solve them exactly, to found analytic expressions for the ground state. And you can check that the ground state has the properties that you need for quantum computation. But that's not typical. Most models would not be exactly solvable at all. Or if they were exactly solvable, you wouldn't be able to check that they have the right properties. So what I'm going to be telling you about today is a result that shows that you can take this simplest model, the cluster model, you add on perturbations into the interaction Hamiltonian, and what you end up with is a model which still has a ground state, which is a resource for quantum computation. Okay, so let me just talk about the sort of traditional formulation of quantum computation with circuit model. So the idea is you have qubits, represented by DOS. You can think of a qubit as a spin 1/2 particle. It's a two-level system. Then you apply gates, which are sort of unitary evolutions on those qubits, create an entanglement along the way. So you can represent a quantum circuit by a quantum circuit diagram. So here's a quantum circuit diagram. The horizontal direction represents time. Each horizontal line is a qubit, and then we have gates acting on those qubits. So here's a C0 gate acting on qubits 1 and 2, and so forth. So the problem is that gates coupling two different qubits, in many implementations, they're harder to implement than just single qubit operations. So we can ask the question, can we do quantum computation using only single qubit operations? In particular, can we do it just by doing measurements on single qubits? Now, measurements on single qubits does not create entanglement, and you need entanglement for quantum computation. So the idea is you need a starting state which is entangled. And so if we have a starting state which has a property, but by single qubit measurements acting on it, we can do quantum computation, and it's called a universal resource for measurement-based quantum computation. And so in particular, it was shown in 2001 that the 2D cluster state is a universal resource that has this property that you can use it for quantum computation using only single qubit measurements. So let me say what the 2D cluster state is. It's called 2D because it's defined on a 2D lattice, 2D square lattice. Each circle here is a qubit. And then the cluster state can be defined as the unique +1 eigenstate of some cluster operators, which take this form. It's basically X acting on one qubit and then Z acting on all the neighboring qubits. And here by X and Z, I'm talking about essentially the Pauli spin operators. So that's the cluster state. So let me explain how you do measurement-based quantum computation using the cluster state. Well, the idea is you show that for any quantum circuit, you can achieve the same thing by measurements on the cluster state. So there's a mapping between quantum circuits and measurements on the cluster state. And so here's the measurement sequences that you would do on a cluster state to simulate this circuit. Here, so Z means you measure in the Z basis, X measure in the X basis. So you see that the shape of the pattern of measurements is very much the same as the shape of the circuit. So for each gate in the circuit, there's a corresponding sequence of measurements that you do on the cluster state. And so here the horizontal direction represents time. Here the horizontal direction is actually a spatial direction in the cluster state, but you can think of as simulated time because it corresponds to time in the circuit model. And so a key feature of these models, of these protocols, is that some of the measurements are adaptive. There are some qubits, such as the one I've marked by a question mark here, which you cannot predict in advance which basis you're going to want to measure in. The measurement basis for this qubit will depend on the outcomes of the measurements on some of these loss of qubits. So this is a key feature. Okay, so that's how you do measurement-based quantum computation using the cluster state. So I still haven't answered the question of how do you create the cluster state in the first place. Well, you could create it using 2-qubit gates, but the problem with that is, well, I just told you, the reason we want to do measurement-based quantum computation is because 2-qubit gates in general are hard. So I'm going to talk about it a different way, which is basically this idea which I alluded to earlier, that the cluster state is a ground state of a local Hamiltonian. Since the cluster state is the unique +1 eigenstate of these operators, if we try an H equals minus the sum of all those operators, then the cluster state is the unique ground state of that Hamiltonian. And then there's a finite energy gap to the next highest energy state, which means that at low temperatures, the state will be in the ground state of this Hamiltonian, which means it will be in the cluster state, which means you can use it for universal quantum computation. And so these terms in the Hamiltonian are 5-body interactions, so you may object that this is not very realistic, and it's not, but people have done more work on this, but I'm going to be talking about just this model for simplicity. Okay, so now that we have the Hamiltonian, now that we have the cluster state as the ground state of a local Hamiltonian, well, the problem, the thing is that this Hamiltonian has quite very special properties. So all the terms in this Hamiltonian commute, so that makes it very easy to find what the ground state is, but it also makes it a very special Hamiltonian. So we want to sort of consider what happens more generically. So consider what happens if we add a perturbation. In this case, the perturbation is just a uniform magnetic field pointing along the x-axis. Okay, so at b equals 0, this term goes to 0, so you just have the cluster state as the ground state. At b equals infinity, this term dominates, and so you have just the dominating interaction is just a magnetic field along the x-axis. And so the ground state is just all spins aligned with a magnetic field. So that's a product state. It's not entangled. So that is useless for quantum computation. So somewhere between b equals 0 and b equals infinity, your ground state stops being useful for quantum computation. Now, in between b equals 0, there's some quite non-trivial behavior which occurs. You certainly don't have commuting terms anymore. You even have a very non-trivial thing at b equals 1, a phase transition. And so we'd like to sort of say something about this more non-trivial Hamiltonians in the middle. Do they still have ground states which are universal? And so what I'm going to show you today is this result that there is a finite region here such that the ground state is universal. So for b less than epsilon, where epsilon is some threshold, the ground state is universal. Okay. So I estimate that this threshold epsilon is approximately 10 to the minus 6. It's not a very large number, but at least it's not 0. And so I introduced this perturbation of a uniform magnetic field just for illustration. Turns out the argument works for all perturbations with respect to certain symmetry. And I'll say some more about why you need that symmetry and what that symmetry is in a moment. But let me just give a general outline of how you establish this. Well, we know that for each quantum circuit that you want to simulate, there's a corresponding measurement sequence on the cluster state. So how my proof is going to work is that basically, if you have a perturbation for a resource state due to the fact that you've changed the Hamiltonian, then that's going to correspond to a circuit, but a circuit which is not precisely the circuit that you wanted to do. It's a circuit with noise. So we know that if you were actually implementing the circuit model directly, you would not be able to isolate your system completely from the environment. So there would be interactions with the environment, messing up what you want to do. So this is noise. And this is exactly the kind of thing you get mathematically from this correspondence. So when you have a perturbation of a resource state, it corresponds to a noisy quantum circuit. And in particular, if your perturbation is a sum of terms acting locally, as it should be if it's physical, then your noise is going to have no correlations in space or time. And so that's a particularly nice kind of noise. It's the kind of noise that's been considered extensively in the theory of quantum error correction and fault-tolerant quantum computation. So what these techniques have been developed to allow you to get around the effects of noise in the circuit model. And the culmination of all this theory is the sort of so-called threshold theorem, which says that there exists a threshold such that as long as the noise strength is less than that threshold, you can still achieve universal quantum computation using the circuit model. But because we have this correspondence, which I'm going to establish, then that we can carry that over and show that there exists a threshold for perturbations to a cluster state. But this correspondence is actually quite non-trivial to establish, and so the rest of my talk is basically talking about how you achieve that. And I'm going to express it mostly in the context of a 1D cluster state, which is similar to the 2D cluster state, except it's on a line. Again, it's the ground state of a local Hamiltonian. So if you ask, what can you do with measurements on the 1D cluster state? Well, it turns out you can simulate circuits which just consist of gates acting on a single qubit. And now, you can't do universal quantum computation using gates acting on a single qubit. So therefore, you can't do universal quantum computation by measurements on the 1D cluster state. The 1D cluster state is not a universal resource, but it does serve as a useful testing ground for ideas and serves to illustrate the more general case in a simpler special case. So it turns out that the cluster state has a symmetry. It's invariant under this symmetry operation, where you apply x to every second qubit. So you can think the action of x here as being a rotation by pi about the x-axis. And so you do that to every second qubit, that leaves the cluster state invariant. Then you can do it to every second qubit, but for also qubits. And so these two symmetry operations generate a symmetry group. It's Z2 cross Z2, which is one of the simplest groups you can have. It's just 4-element abelian group. And so it's just those 4 elements are this one, their product, and the identity. So that's your group. Now it turns out with respect to this symmetry, the cluster state has a property which we call symmetry-protected topological order. And so what do I mean by that? Well, let's go back to this case of the cluster Hamiltonian plus a uniform magnetic field. So recall that at b equals 1, you have a phase transition. And so what people normally like to do when considering phases and phase transitions is they like to say that in this phase, for b less than 1, there's some kind of ordering which this phase has, which a product state doesn't have. And so that ordering is why you have to have a phase transition, because you have to destroy that ordering, and the only way you can destroy that ordering is by a phase transition. And so the sort of standard example which you could talk about in the context of this would be spontaneous magnetization. You can't get rid of spontaneous magnetization without a phase transition. So this phase does not have spontaneous magnetization. What it does have is this much more subtle kind of ordering, which has only recently been understood fully, and it's called symmetry-protected topological order. But what the implication of this is that for any perturbation here, it doesn't have to be a local magnetic field, as long as it respects the symmetry, that you will have a phase transition somewhere between the cluster state and the product state. So you have a symmetry-protected phase. Okay. So the kind of ordering which you actually have in symmetry-protected topological order is quite subtle, but it turns out that there's an interesting way of understanding it which is closely related to measurement-based quantum computation. So that's what I'm going to talk about now. So we know that the 1D cluster state, the unperturbed 1D cluster state, has the property which we can sort of call by the name long-range entanglement, which is basically if you take a finite cluster state on a finite chain, you measure all the qubits in the middle, but not the ones at the ends. You can choose the basis for that measurement such that no matter what the outcome of that measurement is, at the end of it you'll have a maximally entangled state between the ends. So you can always localize a maximally entangled state on the ends, no matter how far apart those ends are. And so what I realized is this is actually a manifestation of this property, which we call symmetry-protected topological order. So what that means is that throughout this whole phase, which we know has symmetry-protected topological order, it also has long-range entanglement. Where am I? Okay, so now I'm going to explain in a bit more detail how this correspondence works. So this slide is, I called it technical interlude because it's a bit more technical than the rest of my talk, so you're warned. So the idea is that if you look at what form the symmetry operations take on the edges, so I basically told you what form the symmetry operations take in the bulk, but what form do they take on the edges? You have a look at the action on the symmetry on the edges. And you might think that it's a representation of the symmetry group, a representation of Z2 cross Z2, but it's not. Z2 cross Z2 is an abelian group, whereas here we have X and a Z, and they anti-commute, they don't commute. So it turns out what you actually have is a projective representation of this symmetry group. So it's like a representation except for global phase factors. So here we have a global phase factor of -1, for example. So it turns out that according to this general characterization of symmetry predicted topological order, this projective action of the symmetry on the edges is the hallmark of symmetry predicted topological order. And so now I'm going to use this fact that the edges transform projectively under the symmetry to show that we have long-range entanglement. So in particular, we know that the ground state has to be an eigenstate of the symmetry operations. And so now we're going to measure the clusters, the qubits in the middle. And we're going to measure in a basis such that these operations, the one I've highlighted in red, are diagonal. And because they commute, we can always find such a basis. And so we get some measurement outcomes. So say we get +1 and -1. So what that means is that now the state after measurement satisfies these correlations. So if you know anything about stabilizer states, you will immediately see that the only way this can be true is if the state after measurement is this particular maximally entangled state. So we've localized the maximally entangled state on the edges. So if you look at what is it about this argument, how does this argument work? It actually, you can generalize it to any abelian symmetry group, not just Z2 cross Z2, using arguments involving Schur's lemma. And so this connection between symmetry-protected topological order and long-range entanglement is very general, and I think it gives you a very nice way of understanding what is it about these symmetry-protected phases which makes them different from product states. Well, it's the fact that they have long-range entanglement, which you can localize over arbitrary distances. Okay, so why am I telling you this, apart from the fact that it's interesting in itself? Well, once we talk about measurements acting on the cluster state, we're getting very close to measurement-based quantum computation, what you would do if you wanted to do measurement-based quantum computation. And so, so now we have this property related to measurement-based quantum computation, and we've shown that it persists throughout this whole phase. And this is the case even though we can actually solve analytically for the ground state here. Just from the properties of the Hamiltonian, the fact that it's in this phase, you know something about how measurement-based quantum computation works on these states, ground states. So we can be even more explicit about this link between long-range entanglement and measurement-based quantum computation. So it turns out if you ask the question, what is it about the structure of entanglement in these long-range entanglement states that allows for long-range entanglement, it turns out it's essentially the same thing which allows for operation of the identity gate. So what I mean by that is if in a circuit model, if you have a circuit which just has a qubit with nothing happening to it, we translate that into the measurement-based model. It turns out that it corresponds to measuring everything in the X basis. And so what I'm saying is that throughout this whole symmetry-protected topological ordered phase, we have perfect operation of the identity gate. So, okay, so this is getting very close to what we want, which is relating properties of the Hamiltonian to properties of measurement-based quantum computation without having to actually solve for the ground state explicitly. But obviously, we want to do more gates than just the identity gate. So if we do a gate which is not the identity gate, then it's not going to work perfectly. That's why I said that it's going to, the perturbations of the resource state are going to lead to noise in the circuit model. So now I'm going to explain a bit more about how we achieve this mapping, which I alluded to. So it turns out that, although I'm not going to go into the details, as long as you have this symmetry, then you can show that you have, if suppose you have the cluster state, and then you're doing some adaptive measurement protocol on the cluster state in order to do measurement-based quantum computation. So it turns out that this is equivalent to doing a different process on a different state. So we have I call it a dual process acting on a dual state. So the dual process is a lot simpler than the original process. The dual state still has the same nice properties as the cluster state. So So this is going to let us actually construct a mapping between the noise model. So I'm not going to go into the proof of how this correspondence works, but it's again based on this connection between symmetry, predicted topological order, and projective representations. And there's quite a few steps involved there. But okay, what's important is what we can do with this mapping, this correspondence. And so consider a circuit in the circuit model, which just has two gates, A and B. And then there are certain qubits which you would measure in the resource state to corresponding to those gates. And we've shown them in red here. So now, suppose you introduce a perturbation into the resource state due to the fact that you've added some term in the Hamiltonian. But that term is a sum of local terms. So it's a local perturbation. Then this will be a local perturbation. It will perturb locally. So what this means is that the perturbation acts independently on these two red qubits, as long as those two red qubits are far enough apart. And so what this then corresponds to is that the noise in the circuit model acts independently on gates A and gate B. So there's no correlations in time in the noise. You have a noise acting on gate A and noise acting on gate B, the noise being associated with the fact that you're doing measurements on a state which is not exactly the cluster state, but it's uncorrelated in time. Okay, so that's all I'm going to say about the 1D cluster state. Now, it turns out in the 2D cluster state you can make similar arguments, but the symmetry group which you need in that case is not just Z2, it's actually Z2 cross Z2 cross Z2 cross, there's also Z2s there. And so that's because you have many symmetry operations. You have, for each diagonal in this 2D cluster state, you have a diagonal strip of x's. And so there's one symmetry generator for each of these diagonals. And so if you have this symmetry, then you can make similar kind of arguments as the ones I sketched out in the 1D cluster state. And so in particular, you can, using the kind of locality arguments which I talked about earlier, you can show that local perturbations to the resource state correspond to uncorrelated noise. And this allows you to get the threshold result. And so I apologize, I actually have to, there's something important which I had to say on this slide. Sorry about that. So we do really need to apply the locality argument in the dual process. The reason for that is that in the original process, you have measurements. The outcomes of measurements on some qubit here can influence the measurement basis all the way out somewhere else. And so you have no locality in this process. There's no locality argument you can make for that process. But with this process, because it's so much nicer and simpler, you can make a locality argument. So that's why you definitely need a symmetry in order to make this argument work. So now, let me return to where I started, this idea that you can have systems which, in equilibrium, have the entanglement that you need for quantum computation. And so you don't have to make the entanglement. Your system the entanglement just appears in equilibrium. And so people have talked about this idea for a while, but the problem with the thing about all these models which people have talked about is that they're specifically constructed so that they have the special properties that you need in order to be able to analyze the situation analytically. But those special properties are not at all typical of interacting quantum spin models. So what we'd like to be able to do is show that a Hamiltonian has a ground state, which is a universal resource, without having to actually find that ground state explicitly. Just by looking at the properties of a Hamiltonian, you should be able to deduce, for example, the fact that it's in some phase, you should be able to deduce that the ground state is a universal resource. And so what I've shown you is sort of a step towards that goal, because what I've shown is that as long as you have some Hamiltonian which respects of symmetry and which is close enough to the cluster Hamiltonian, then its ground state will be universal. Okay, thank you.